Good evening, everyone, and welcome back. Tonight, I'm here, Jamil Siddiqui, here with you tonight to go over polar coordinates and their role in calculus. If you can hear me and everything's coming through okay, if you give me a thumbs up over in the chat, that would be great because I want to get started. I want to make sure we're all on the same page. Thanks for joining us. We're going to be looking at polar coordinates and where they get used in BC calculus and really how to kind of explain them to your students so they get a good understanding of what they are, and so that they'll really understand them and try not to memorize so much, but have a firm basis on what's going on. So, all right, I see Jenny and John, you guys are with me, so this is great. We're going to keep going. We've got a small group tonight. Any questions you guys have, put it over there in the chat. I'm happy to take a moment and just go over anything you guys are really concerned about. So, let's see here. Remember, as always, follow Fiveable on all of our social media sites. You can get updates as to what we're going to be streaming and what topics we're going to be covering each and every week so that you can get your students prepared. Tonight in this stream, what I'm going to focus on is just kind of an introduction to polar coordinates, what they are, and how we can get our students to really, like I said, understand them. We're going to look at polar functions and slope, and what does it mean to find the slope of a polar function. We're so used to finding slopes of rectangular functions. Does it work the same way with polar? We're going to take a look at that. And then, of course, how do you do area and do it with polar functions and do it correctly? And those of you who teach AB calculus, you know a big portion of the subject is about finding slope, finding area. But we're always doing it with rectangular coordinates. Once we make the move to BC, we open that up a little bit more. We start talking about a polar coordinate system, and we really want to get an idea of what's going on with that. So what I'd like to do to start is just take you guys through a brief discussion as to what polar coordinates are and where they come from. So let me just switch over to my tablet here. Okay. And when talking about polar coordinates, or really what we need to do is go back and talk about rectangular coordinates. You know, if you talk to your students about what rectangular coordinates are and you say, how long or what's a point in rectangular coordinates? And that's going to be a question that your students are going to think that they have the answer to right away, but do they really understand? So when you say, hey, look at the point 4,7, what does that mean? Now, every student will know exactly what to do. They'll go over 4 to the right, they'll go up 7, but do they understand what they're really finding there? And one thing we've got to stress to them is that a coordinate point is nothing more than a location. It's a location somewhere on that axis, on the XY grid, okay? So even in polar coordinates, it's the exact same thing. What we've got right here is we've got the Cartesian coordinate system right there. And what we want to do is we want to talk about how to get to a location on that Cartesian coordinate system. So, for instance, if I wanted to get to this point right here, okay, what we're very used to is the idea of rectangular coordinates. And rectangular coordinates would tell you how far to go to the right, and then it would tell you how far to go up. And if you were walking along that path, you would end up at this point. But if you were actually standing there out in the middle of a field and you were standing here and you wanted to get to this point, you probably wouldn't follow the rectangular path, okay? You would probably just make a straight line for it. So the idea of polar is to say, from where we're located, if we're facing this direction right here, and this is called our 0 angle, how far do we have to turn this way so that we line up with this point? And then how far out do we have to walk to get there? And that's really what polar coordinates are all about. So we're going to start by kind of breaking this down and really looking at a rectangular beginning and showing how a polar coordinate system can be made from that. So again, let's just pick a point here, an arbitrary point in the first quadrant. We all understand this point can be labeled as x comma y. But again, if you think of those just as directions, okay, we're going to go over to the right this distance, which we're going to call x, and then we're going to go up this distance, which we're going to call y, and that tells us how to get to that point. Now, if you were going to walk in a straight line to get there, you would draw this, and that would automatically create an angle that we're going to label as theta. And we have a hypotenuse there, and we're going to call that r. Okay? So to me, rectangular coordinates is all about horizontal movement and vertical movement. Go left or right, go up or down, get to that point. polar coordinates is really about the idea of trying to run around in circles. I mean, that's really what it is. You're stuck on a circle, and how do you move from one coordinate to another? By moving from one circle to the other. So that's why we're using r. R is going to be the radius of this circle, and we'll see a little more about this as we go through this evening. But the first thing that we should do is we should really just do some basic trigonometry on this drawing and really get some relationships between x and y, which we're all familiar with, and see where r and theta come into play. So, for instance, one thing that everyone's going to see right away in this is they're going to say, well, we know x squared plus y squared equals r squared. So this is giving us a relationship now between our rectangular coordinates and our radius, which is one of our polar coordinates. Along with that, you could say pretty quickly that the tangent of theta, which would be the opposite side over the adjacent, is going to equal y over x. These are the two equations that are going to work together so that if we have a rectangular coordinate, we can change it into a polar coordinate. The two coordinates in the polar system are r and theta. If you tell me what angle to rotate to, and then the r to walk out, I can get to that point that you described using x and y. So if you're giving me a point in x and y, I can use these two equations here to find out what the r is, find out what the theta is. A lot of textbooks will take these one step further. They'll solve it for r, and they'll say that r is equal to the square root of x squared plus y squared. And then they might go and say, well, that theta is equal to the inverse tangent or the arctangent of y over x. When I do these with my students, to be honest with you, I actually just leave them with these equations right here, and then they can solve these as necessary. So I don't make a big deal about solving these for r and theta. I like the first two equations. I feel like my students are most comfortable using those to begin with. So now that's what happens if we've got the x and the y, and we want to find r, and we want to find theta. What if it's the other way around? What if they give us r and theta, and we want to find x? So if you go over to our triangle on this one, if we have r, and we have x, and we have theta, and you look at those three things in the triangle, really what they're telling us is we've got an angle, we've got an adjacent side, and we've got a hypotenuse. So every student who's taking BC Calculus is probably ready to say, well, if you've got the adjacent and you've got the hypotenuse and the angle, that's a situation where we're going to be thinking about using trigonometry. We're going to be thinking about using cosine. So again, not going straight to the final result, but more building it. My students will be very, very inclined to say that cosine theta equals the adjacent side over the hypotenuse, and they'll get this cosine theta equals x over r. From there, if we want to do y and bring that into the mix, now we're going to be using the opposite side and the hypotenuse. So that would be sine theta equals y over r. You might be wondering why not use tangent in this one. Remember, in these two equations, the idea is that we start with a polar coordinate and we're trying to get to one of the rectangular. So I've got r and theta as my two polar. I'm using x as the first one in the first equation, and I'm doing y separately in the second equation. Once I've got these equations built, again, I can manipulate these. I can solve these for x and for y. So if I solve the top equation for x, what we're going to get is x is equal to r cosine theta. And then down at the bottom, we're going to get that y is equal to r sine theta. Now, these two equations I do stress with my students. I do make sure my students are very, very comfortable with these two equations, but I don't have them memorize them. I want them to know where they come from and derive them just by using our simple trigonometric definitions of sine and cosine. If you can do that, you'll never forget these two equations for x and for y. So now if you give me an r or a theta, I can tell you what x coordinate I'm standing at, and likewise I can tell you what y coordinate I'm standing at. So again, these four equations, whichever forms you choose to use of them, kind of important for your students to have a good handle on these and be ready to go. So the first day I talk about polar, I don't start with any of this. I'm just doing this right now for the background to get it out of the way. When I start with polar, I tell a story about when my town built a new school. So 7 years ago, we built a new school in my district, and I tell the students how they asked all the teachers for designs for the school, which of course they really didn't, but it makes for a good story for my purposes. And I tell them I submitted this design for the school. And the reason for this design is quite simple, that this school is based on calculus being the center of the universe. We were going to put my classroom right in the center, and this would be the calculus room right here. And we would build the school around calculus, and that would be the idea. And there would be one inner hallway, which is right here, that would go all the way around. I'm sorry, that's the outer hallway. And one inner hallway right here that would go all the way around. then all of these rooms would be labeled by their numbers, and so on. Okay, so those will all be 101, 102, 103, going all the way around. This outside could be 201, 202, 203, going all the way around, and so forth. And then I say, okay, if you wanted to direct a student from my room, and the door to my classroom is right here. If you want to direct a student from my classroom out to room 103, how would you tell them to get there? And my students look at me and they're like, well, you go out and you turn right until you get to 103. And I say, well, okay, but let's say there are no numbers on the doors yet. The building's brand new. Students are still not familiar with it. How would they know where to stop if it wasn't labeled? And because they have seen this in trigonometry so many times, because when we do trigonometry, we are always talking about finding our trig values, using the circle to do it. They're very used to the idea that this up here is pi over 2. So my students will tell you, we're going to go out one hallway, and we're going to go through a pi over 2 rotation. And when we get there, we're going to stop, and that's going to be where room 103 is. And they tell me it's going to be the first hallway, pi over 2 rotation. And now I've told them, or they've told me how to get to a location using a distance along an axis, going one straight out to the right, and then rotating pi over 2. Likewise, I say, okay, now let's say I want to go out to room 202 this time. How would I do that? Well, they're like, okay, you're going to go through this doorway here. You're going to go through this hallway all the way out to here. That's going to take you to the second hallway. And now you've got to rotate up to this location. And this location, and they'll estimate it, and it's fine. As long as it's reasonable, I'm perfectly happy to accept their answer. And they might tell me this is pi over 3. So now they'll say, well, we got to go 2 and pi over 3. And that will get you to room 202. So they're starting to understand now that, okay, we can use distance along that horizontal axis and then a rotation to get me to a location. So now I say, okay, what if this was the main office out here? Okay. And we have the restrooms down here. And a student asked me, can I go use the restroom? And I say, okay, well, what would the directions be to go to the restroom? Well, second hallway. So we would want to jump back out to that second hallway to get to the restroom. But now, do we really want to rotate following the same pattern? Because, this would be pi over 2. This would get to pi eventually. Down here would be 3 pi over 2. And then all the way back would take us back to, let me make some space there. Going all the way back around, this would be our 0 angle, but it would also be our 2 pi. So if I wanted my student to get to the restroom as quickly as possible, I don't know if I would send them 2 and then 3 pi over 2, because that would have them rotating all the way around the outside hallway in this direction. So I asked my students, okay, is there an easier way or a more efficient way for my student to get there? And now, without hesitation, they're saying, well, we just want to rotate the other way. Can we call that negative pi over 2? And sure enough, that's exactly what that would mean. It would mean to go out 2 hallways and then rotate pi over 2 in the other direction. That would get them there. So then I always ask the students, okay, and you may or may not have a student like this in your own school, students who like to wander the halls. If you had one of those wandering students, what directions might they follow to get to the restroom? And all of a sudden, students are thinking, because they're saying, well, they'd probably go out this way. And then a lot of these students go all the way to the restroom, and they're like, no, I need a little bit longer of a break, so they go around again. Well, if they were to do that, what would be their directions to get there? They're still going out to the second hallway, but this time they're going a full 2 pi all the way around, plus another 3 pi over 2. So they're going to go a 7 pi over 2 to get there. And very quickly, students start to see there's more than one way to name a location in polar coordinates. Just by asking all these different ways to traverse the map of the school, they can all come up with different directions to get to any room, whether it be in the inner circle or the outer circle. But they're starting to see that polar coordinates are not just a location, they're also directions on how to get to that point, which is a pretty important distinction to make. So what I'd like to do now, and feel free to jump in, ask any questions, any comments. If you have anything in particular you'd like to talk about this evening, just put it over there on the chat. I'm more than willing to discuss things that you guys are interested in hearing about in polar coordinates tonight. But where I'd like to go next is I'd like to talk about, okay, what does it mean to graph a polar function? Okay. And one thing students are going to struggle with, at least my students struggle with, is the idea that no matter if we're dealing with polar coordinates or rectangular coordinates, this is always considered the x-axis. This is always considered the y-axis. The polar coordinate system is superimposed on top of the xy axis. So we still have this idea of a horizontal measure, the x-axis, and the vertical measure. They're still there. It's just that we might not be moving horizontally and vertically to get to our points. So when you ask students, let's graph a function, and we're going to look at the polar function 1 plus cosine theta to start with tonight. How do we take that and translate that into a polar graph? Well, what most people do to start with, I know I did this when I first learned polar coordinates, and I still make my students do it today. Let's make a table, and let's just find out what's happening. And we choose values that we like. So we might plug in 0 for theta, because that's our angle, and the cosine of 0 is nice. You might do something like a pi over 4. You might do something like a pi over 2. Maybe a pi goes in there. Any of those special angles your students can make. And then you can start plotting points and connecting the dots to create this polar function. I find value in that the first day, letting my students do that. I think it's important they get to see how points are plotted and all that stuff works. But I got to be honest, I do not want my students continuing with that method after the first day. I think there's a much stronger way of doing it, and I'm going to show you that this evening, and I hope you'll agree. I'm going to draw 1 plus cosine theta, but first I'm going to take it down here and make it what I'm used to. And that's f of x equals 1 plus cosine x. I'm going to pretend it's a rectangular graph, because if I can understand how the rectangular graph works, that's going to give me a lot of great insight as to how the polar graph works. Now, 1 plus cosine theta, my students will be fairly familiar with this because this is our cosine graph raised up by 1. So instead of starting at 0, it's going to start on the y-axis with a y-intercept of 1. And I'm sorry, it's going to start at an intercept of 2, because cosine usually starts at 1. It's going to go up to 2. And then it's going to draw that cosine wave that we're all familiar with, just raised up by 1. So the period will be 2 pi. The halfway point will be pi. We'll get a pi over 2 halfway in between there. And then using pi over 2 as a marker, that's 1 pi over 2, 2 pi over 2s. That would be 3 pi over 2 to get there. And we know that those values are at the coordinate 1, and this is at the coordinate 2. This, to me, is the key to graphing the polar graph. Because now, this is really just like saying the relationship between r and 1 plus cosine theta. And what this means is, if I think of this now as a theta axis, I'm sorry, as an r axis, and think of this as a theta axis, I know when theta is 0, the radius is 2. Which means now when I go to the polar graph, and one thing I do have my students do in the beginning and make sure they're familiar is that this is always going to be 0 as theta. This is pi over 2, pi down over there, 3 pi over 2 over here, and this will also be 2 pi when I come all the way around. So when I start talking about the point 0, 2, okay, 0, 2. That means to rotate 0 degrees and walk out 2 steps. So all I'm doing is going 1, 2, and I'm putting my first point right there. Okay, so that corresponds to this point right here. So from here, what's going to happen is I'm going to try to chunk this a little bit. And what I mean by that is I am now going to follow the graph from theta equals 0 to theta equals pi over 2, which is this part of the graph right here. What that's telling me is the radius is starting at 2, but as I rotate through my angle, my radius ends up at 1. So to translate that, what it means is, and here's the other thing I want to stress. I said earlier, now is a really important time to really get an idea of what I mean. Left out of its own devices, a polar coordinate just wants to go around in a circle. I've started this guy with a radius of 2. If he had his way, the way I think about polars, if he had his way, he would continue around this circle of a radius of 2 all the way around. And he would just keep going all the way around, keeping that radius 2. But the fact of the matter is, the radius isn't staying 2. The radius is dictated by this equation right here. So what's happening is the radius is starting at 2, and by the time it gets to pi over 2, the radius has been sucked down to 1, and that's this value right here. So what it means in this graph is by the time I rotate from here to here, my radius is going to start at 2, but by the time it gets to pi over 2, it's going to be at a value of 1. So it's going to continue to get kind of drawn in, so to speak. So it's going to look something like this. All right. Left by itself would end up at a value of 2. Because it's being pulled in, it's going to now be at this value of 1. So now what I want to do is I want to go and I want to look at the next piece of the graph. I'm going to try to color coordinate this for you guys so it'll really stick out. I now want to look at what happens between pi over 2 and pi. So what we're talking about this time is rotating through this quadrant, pi over 2 and pi, but what is the radius doing? It's starting at a value of 1 right here, and by the time it gets down here, that radius is shrunk down to 0. So the theta value is pi, and the radius value is 0, which means instead of this continuing with a radius of 1, by the time it gets to pi, it has to shrink all the way back into the origin. So that is kind of the thought process that I have as I'm graphing this. I'm just using the rectangular graph to dictate what the polar graph looks like. Once you see this, we're going to continue the exact same way going on the other side. So now this time, I'm going to break it from pi to 3 pi over 2, which is basically going to take us from here to here. Over in the polar situation, that means we're trying to rotate from pi to 3 pi over 2, so we're going through that piece. But what's the radius doing this time? It's starting with a value of 0 at pi, but by the time we get to 3 pi over 2, it's now going to have a radius value of 1. So we're going to rotate through this third quadrant, starting with a radius of 0, but it's going to jump back out to 1. And that's going to take me to that value, which looks like, and it is, -1 on the y-axis. So the final piece of the puzzle here, we're going to go and we're going to take and look at this thing from 3 pi over 2 to 2 pi, which is that piece. When we get to the end, that radius is now gone out to 2 pi comma 2, which means when I rotate through this last piece, I've got to start with a value of radius 1, and I'm going to end with a value of radius 2. So it's going to continue to rotate back out and complete this shape like this. So this shape right here is the shape that this particular polar function makes. So again, my thought on this is, how do I use the rectangular graph to dictate what the polar graph is doing? And if you just picture this rectangular graph in the following way, if my graph is decreasing, it means my radius is decreasing. So it's getting pulled closer to the origin. So everywhere from here to here, the radius is decreasing, and it's getting pulled closer and closer to the origin. If my graph over here is increasing, then my radius is increasing. So everywhere in the second section, increasing. And you see as we rotate from pi to 2 pi, that's exactly what happens. That radius gets longer and longer until it goes back out to a value of 2. I'd like to do just one more graph with you guys because I want to talk about negatives, because that's something that students struggle with. So we're going to look at this one real quick. It's r equals 3 sine 3 theta. If we graph this to start with, we're going to get something that looks very much like a sine wave with just a different period. So this graph is going to look something along those lines. To find the period of this, we'd set our angle equal to 2 pi, and that would tell us that theta would be 2 pi over 3. So we know this is 2 pi over 3. We know this is pi over 3 because it's halfway. Half of that would be pi over 6. And then this would be 1 pi over 6, 2 pi over 6. That would give us 3 pi over 6s to get there, which is really just pi over 2. And because we're multiplying that sign by a factor of 3, we're going to go up to 3, positive there, and down to -3 over here. So by using this graph, the idea is we're going to be able to create the polar graph. So let me just move that over a little bit so I have a little more space. Okay, so we're going to start at 0. This is still going to be pi over 2. We're going to have pi over here, 3 pi over 2 over there. And now we're also going to have 2 pi here. And because our values are kind of broken up in between 0 and pi over 2, I'm going to put a couple more values in there. I am just going to draw a dotted line right here, and that will represent pi over 6. And then I'm going to represent pi over 3 with the dotted line up there. Okay. So now what I'm going to do is I'm going to break this into smaller sections. The first section I want to do is going to be the section of this graph that goes from 0 to pi over 6. So in that section, we start with the value of 0, which means we're going to start right at the origin. And by the time we get to pi over 6, by the time we rotate through here, my graph is going to have to go out to a value of 3. So it's going to have to rotate out pretty far out to 3. The next piece we're going to look at, we're just going to take this guy from pi over 6 to pi over 3, which is this piece of the graph right here. Well, in the polar graph, that's going to rotate through this region. And what's going to happen to my radius is it's going to start at a value of 3 right here, but you can see it's decreasing, and it's going to decrease to 0 by the time I get to the pi over 3 rotation. That means it's going to have to come back in basically the exact same way it went out. And that's going to give me my first loop. So I hope you see how these two correspond. The next piece I'm going to look at is I'm going to look from pi over 3 to pi over 2. Now, this one's a little tricky, I'll be honest, because I want to rotate through this sector right here. But what we've got to be aware of is that we're getting negative values. So every one of these angle lines I'm drawing right now is kind of like an axis. This entire line right here, I'm going to highlight, I consider that the pi over 6 axis. Okay. If I move towards pi over 6, I'm moving in the positive direction. If I move away from pi over 6, I'm moving in the negative direction. This guy right here, I consider the pi over 3 axis. So I move towards pi over 3, that would be positive. If I move away, which would be going to the third quadrant, that would be negative. Every angle axis can be thought of that way. So as I go to rotate through the pi over 3 to pi over 2, which is this portion right right here, as I go to do that, what I want to make sure is I'm doing it in the right place on my polar graph. So this is telling me to start with a a radius value of 0 at pi over 3. And by the time I rotate out to pi over 2, I've got to get out to a radius value of 3. Now, your students are going to want to put this in this quadrant right here because they're seeing that as pi over 3 to pi over 2. But because all of our answers are negative, they're actually going to show up on this side. So what's going to happen is instead of looping in this quadrant in some way, I'm actually going to go from 0 to 3 down in that opposite space because I'm in that negative version. Students are going to struggle with that. My students struggle with this every year, but after they do a couple of them, they start to understand it a whole lot better. We're going to continue really doing the exact same thing. We're now going to look at pi over 2 to 2 pi over 3. And when I look at that one, we're going to get this piece, which means my radius is going to start at 3 and go back to 0. Really, it's negative 3. So instead of rotating through, and let me draw some more angle axes here. Let me put 2 pi over 3 in here. So there's 2 pi over 3. And let me also just put in 5 pi over 6. So now as we go through, I want to rotate through this region right here, which is the pi over 2 to 2 pi over 3, but I'm going from negative 3 to 0. So instead of showing up in this region up top, I'm actually going to show up in this region down here. Okay, so I'm going to start with that value of 3, and my radius is going to get pulled back to being 0. So it's going to go in like that. Now, the next problem my students always have is they look at this and they think they're done because the rectangular graph starts to repeat at this point in time. If I come back down here and I continue with this rectangular graph, we've got the basic shape. We know it's just going to repeat. It's going to do the exact same shape we see, and it's going to continue in this fashion. Problem is the rectangular period doesn't always match with the polar period. So as we continue with this, I'm doing steps of pi over 6. So that's 1 pi over 6, 2 pi over 6s, 3 pi over 6, 4 pi over 6. This is going to be 5 pi over 6. This will be 6 pi over 6, which is going to be pi. If I continue, I'm going to get 7 pi over 6. And then this would be 8 pi over 6, which would be a 4 pi over 3. So I want to keep going until I make sure my polar graph is going to repeat. So I'm going to continue with this. I'm going to do the next region. I'm going to go from 2 pi over 3 to 5 pi over 6. Now, the nice thing about this is I'm paused it again. So I will show up in this region up here. All right. And I've got to go from 0 out to 3. So it means I'm going to rotate from this line to that guy and get back out to 3. And now I'm just going to go and I'm going to do this next piece from 5 pi over 6 to pi, which again, you can see that it's positive. So we're going to rotate through that little wedge. And we're going to start with a radius of 3 and get pulled back into 0. So that's going to get pulled back right into there. Now at this point, if you continued, what you're going to find out is this time I'm pi to 7 pi over 6, which would be this little piece. But because we're negative, we're actually going to see the reflection, and you're going to see us start to retrace the shape that we've already made. Okay, this is actually called a three-leaved rose in polar coordinates. This is where this shape ends. So you actually have to take it all the way to pi to find the full period until the graph started repeating in the polar graph. So I hope that kind of introduction to graphing makes sense to you guys. This is not something I would do with my students the very first day. This is definitely something I would do after they plotted a bunch of points. They need to plot those negative radius to understand that you're not moving towards the angle axis, but you're moving away from it. So I would make sure that they would do that for a couple of days first, or maybe a day or two. And then after they had done that, then it would be time to try to introduce the rectangular graph and how to combine the rectangular to make the polar. So I hope that makes sense with you guys. So that's what we're going to do for graphing. I'm going to switch back to my slides just for a second. The next thing I want to talk about when you're talking about polar. Okay, is the area question. Now, this is a big question, obviously, in AB calculus with rectangular coordinates. If you look at my picture up there on the slide right now, I've got a rectangular. But here's the thing you want your students to understand. If they understand how it works in rectangular, it works the same way in polar. Math is always the same. If you understand how area works, it doesn't matter if you're doing rectangular or polar. So I feel like if I set them up really well with a rectangular problem first, that will help to generate the polar problem. And the way that we all do rectangular problems is we cut it into shapes we know. So we've all done Riemann sums. We understand that we want to see how many rectangles we can fit into this. And that would be an approximation and not a very good one. But as I go and I make my bases smaller and smaller, I can make my approximation better and better. So the idea is, how do we make a better approximation by using a shape that we already know? It should come as no surprise in rectangular coordinates, we use a rectangle. Okay, that should make perfect sense. In polar coordinates, what shape are we going to use? And how are we going to use it effectively like we do in rectangular? So that is what I want to discuss with you guys now. In order to do that, I'm going to go switch back to my tablet. So if you'll just give me a second. All right. And one thing I want to do real quickly, just very quickly, is I just want to discuss the rectangular version of area, because my hope is if we do the rectangular version well, we'll do the polar version equally well. So the idea is with rectangular coordinates, if you're finding an area, like the shape we just talked about, something along those lines, we would know this guy is f of x, and we would have some bounds on the x-axis from A to B. And I'm looking at my screen. I don't see my tablet filling in. Do you guys see any writing on my tablet? Could you give me some feedback? Because I'm not seeing it now. I just want to make sure you're able to follow along. No, it's not there. Okay. Let me real quickly There it comes. Let me see if it stays with me now. Okay. So now the idea is, can we cut this into shapes we know? So if we cut this into shapes we know, and I literally in my classes, I draw a knife and I start slicing. If we were to cut this into shapes we know, what would those shapes look like? So we're going to start cutting this into rectangular pieces. Well, the question is, how many rectangular pieces are we going to need in order to fill up this entire shape? And this is done in AB Calculus all the time, so we try to get our students to understand the idea of an infinite number of rectangular pieces. So if it's an infinite number, if that's the case, then how do we add them all up? And that is where the integral comes in. So I hope that everyone has, at one point or another, has been working with their AB students, and they've set up an integral for this problem, and they're saying, okay, in order to find this, we have to figure out what we're adding up. And because we're adding up rectangles, and this is how I do it every single time in my classes, I see we're adding up bases times heights. So what are the bases going to be? Well, the bases are defined in a Riemann sum by this guy down below, our delta x. But as that delta x shrinks closer and closer and closer together and becomes, infinitesimally small, we change the notation from delta x to dx. And that's important for all your students to understand. Okay, you really, really want to drive that home, that as we bring those 2 points together, the delta changes from a 2-point difference to the Leibniz notation of dx, which is a 1-point difference. So my bases are dx. Now, how do I find the heights of each of these functions? Well, the function value itself gives them. So we know we've got a height of f of x, we've got a base of dx. The last thing I want to be clear, if we're using a base of dx, I know it's not necessary, but I always write x equals on my bounds. Okay, my tablet catches up. We'll see that come in a second. I want to give my students the idea that, there's consistency. The differential tells us what the bounds are going to be. So one thing I'm going to do right now is I'm actually going to restart my device here because I seem to be lagging a little bit. So give me a second while I do that. I just want to show you this while I'm full screen. One thing I do with my students all the time is I hold up my 2 fingers like this, and every time I do, my students say delta x. They understand it's the difference between 2 points. And then if I want that distance to shrink, I'll go like this, smaller and smaller and smaller. And when I bring it together, my students will then know that they have to yell out dx. And that's how they know the difference between the 1-point slope and the 2-point, or the 1-point difference, the 1-point change, and the 2-point change. So I'm now connecting again. Let's see if this works out a little better. All right, give me just a moment and I'll pull that screen up. All right, so like I was saying, if I've got a dx here, then that's going to give me x equals for each of my bounds. So now the only thing left to do is to ask, where do we start adding? And that would be x equals a. And where do we stop? And that is at x equals b. Unfortunately, that does not seem to be working any better. Let me try to close that one more time. I'm sorry about this. In the meantime, if you guys have any questions, you want to post those, I can answer those while I'm trying to get my tablet back up and running smoothly. All right, so let's take a look at the polar problem. All right, so in this one, the example I want to look at, you're being asked to find the area basically inside the polar coordinate, the graph we just saw, which was r equals 1 plus cosine theta. Unfortunately, that is not working tonight. I'm going to try restarting this one more time to see if we can get it working a little bit better. If you guys bear with me, I apologize. We're having some technical difficulties. I apologize. I'm still trying to get this to restart. I think we might be having it come back here. Hold on. Wow. All right, let's see if we're back here. Okay, so in this problem, we're finding the area of the graph we were just talking about. So the question is, how do we cut this into shapes we know? Now, with the rectangular coordinate, it was simple. You cut into rectangles. If you ask your students this one, how do we cut it? They're inevitably going to say, well, take your knife and cut it along those slices that the angles were on. And they're going to cut it like this, and they're going to cut it like this. And then if you ask them what shape do you get, they're going to come back and they're going to tell you that you're going to get a triangle. And this is where it's imperative that you keep reminding them that in polar coordinates, you're always moving in circles. So I've got an animation I want to show you guys that will kind of help us out with this one. So I want to go back to my PowerPoint. And here we go. Okay. So in this one, what's going to happen is we're going to start with finding the area and asking which way are we going to slice. So there's our shape. And the idea is that we're going to slice along the angles. So there's one slice and there would be another slice. And like I said, your students are going to look at that and they're going to want to say that it's a triangle. But because the edge of that is really moving in a circular pattern, it's not a triangle at all. It's actually going to be a sector. That is the one thing that really is going to drive this whole idea, okay? That the edge of that is not straight. The edge of that is a rounded shape. It's going to be a sector. So as we start looking at this and labeling it better, another thing your students are going to want to do is they're going to want to call the angle between the two slices theta. But remember, in polar coordinates, theta is already defined. It's the angle starting at the x-axis. So this can't be called theta. That's going to be called theta. So we know this is theta, but how do we define that sector? Well, we see the first slice given by the blue. We see the second slice given by the purple. If we call that first angle theta 1, we can then call that second angle theta 2. And now the slice runs from theta 1 to theta 2, and we see it right there shaded in. We're going to end up calling that guy delta theta. Now, if we can get our students here, we're actually going to be in really good shape, because from here, we know that the area of a circle is pi r squared. The area of a sector is the part of the circle we're using out of 2 pi, so delta theta out of 2 pi of that pi r squared. And keeping that in mind, the area of a sector can then be reduced down to 1/2 r squared delta theta. So if we look at that in practice, and going back to my iPad, hoping for the best here as we go back to it, we've now got that this guy from here to here is our delta theta. And the area of that sector, again, just run through it one more time. The area of a sector is delta theta over 2 pi. Write that again. Delta theta over 2 pi times the area of the circle, which is pi r squared. When we lose those pi's, what we end up with is a constant 1/2. Then we've got an r squared, and then we've got a delta theta. So we want to add up an infinite number of these sectors. And what's going to happen is these two slices are going to get closer and closer together. And when they do, delta theta is going to be a 2-point change. And as it moves closer and closer together, delta theta is going to turn into d theta. And for that, we now have what we want to add up. So if we try to set an integral, the general form of the integral in this case is going to be the addition of all of our sectors. And that's going to be 1/2 the radius squared times our delta theta, which is going to be our d theta. And we're always going to start from a 1 theta value to a 2nd theta value. So as we look at this one, if we understand that we're just adding up all those sectors, we now know that the radius in this case is going to be 1 plus cosine theta, and that's given up the top. And now the question is, where's our first slice? Well, our first slice is going to happen right here, and that's at theta equals 0. And then we're going to keep slicing all the way around the circle until we get to the back to where we started, and we're going to go all the way around to 2 pi. That is one answer that would give us the area of this shape, okay? There are others because there's some symmetry in the shape. We could have gone from 0 to pi and then just multiplied by 2. That would have been an acceptable answer. But to me, it's about finding those sectors and adding them together. So if you can get your students to understand that the area of a sector is this delta theta over 2 pi times pi r squared, and then that delta theta will turn into d theta as we cut those slices closer and closer together, your students will have half the problem solved already. So that's my setup for finding area in polar coordinates. The other thing I wanted to bring up this evening is the idea of how do you talk about slope? Because you're often asked to find the slope of a line to a polar function. So here's a classic question. Find the slope of the line tangent to r equals 1 plus cosine theta when theta is equal to pi over 3. My students every year do the exact same thing the first time. They go and they find the derivative of r with respect to theta. So I'll see my students do this all the time. They'll say r prime is equal to the derivative of 1 is 0, derivative of cosine theta is negative sine theta, and they'll leave it like this, and then they'll plug in pi over 3. What your students have to understand is that when we're talking about slope in this problem, we are talking about that classic definition of slope. Rise over run, okay? This guy is still that rise over run, which is always defined by our delta y over our delta x as a 2-point change. But since we're talking about a tangent line, it's actually going to be a 1-point change. So we're really looking for our dy over dx. Because when we draw that tangent line at pi over 3, all right, oops, when we draw that tangent line at pi over 3, we're really talking about this point right here and trying to find the equation of that line right there. Well, since this is still an x-axis and this is still a y-axis, the slope of this line is still given by a rise over run. So we're still looking for dy over dx. Students will struggle with that greatly at first because they see r and theta and they think the derivative is going to be in terms of r and theta. Now, you can take r prime and find negative sine theta, but it doesn't mean the slope the way that we're thinking of a rise over run slope. R prime equaling sine theta tells us how r is changing as theta changes. Okay, so that tells us how r prime is always, are we getting closer to the origin or are we moving further away from the origin? If r prime is negative, then the radius is decreasing and we're moving closer to the origin. If r prime is positive, then the radius is increasing and we're moving further away from the origin. So there's a lot of confusion the first time students see this. I remember myself when I first learned these problems, I really had no idea what I was doing. There was a formula in my textbook, and I just plain and simple, I memorized it. Some of you guys may be familiar because here is that formula. And again, my tablet is not staying with me today. I apologize for this. Let me close out and come back in. And it is frozen once again. Okay, so we're going to do this the old-fashioned way. Here we go. No, I can't even get that to work. Those of you who have been patient enough to stay with me, I appreciate that. I am trying to overcome this and get back on track. All right. I seem to be. Okay, here we go, finally. Let's see if we can get this up and running. All right. So as I was saying, the formulas I remember memorizing in my dorm in college so I could pass my test, so I could figure out how to find the slope of a polar graph are written on the screen there. Um, I later learned after I started teaching, there's absolutely no reason to memorize these whatsoever. Okay. These can be derived very easily if we can just remember our equations from the beginning that x equals r cosine theta and y equals r sine theta. If we can remember these, then we can derive these two equations. Because if we take the derivative of both sides of these equations with respect to theta, what ends up happening is that this guy will become dx over d theta is equal to, and now we've got to set up a product rule for this particular expression. So the way I set my product rule is I take both factors of my function and I take the derivatives individually. The derivative r would be dr over d theta. With respect to theta, the derivative of cosine theta would be negative sine theta. And now to put those together, we would go this direction, which would be cosine theta, dr over d theta, and then it would be plus the other direction, which in this case would be negative r sine theta. And if you look closely, that is precisely the formula that I was given for dx over d theta. And we can do the exact same thing for y equaling r sine theta. Setting up a product rule for this one, it would be r and then sine theta is the two factors. With respect to theta, this would be dr over d theta, and this would be cosine theta. So now the derivative of y will be dy over d theta. And using the product rule over here gives us sine theta times dr over d theta plus r cosine theta, which again is exactly this formula right here. So back when I was a student and didn't understand what I was doing, I forced myself to memorize these. Not necessary. You can actually derive these just by using the product rule and taking these derivatives with respect to theta. So once you know these two expressions, remember, we were looking for dy over dx. So dy over dx ends up coming from the fact that we can take the derivative of x with respect to theta. We can find the derivative of y with respect to theta. Using those two things, we can then find dy over dx by using it as dy over d theta all over dx over d theta. So what happens is we're going to get a derivative, a dy over dx derivative, telling us the rate of change of the horizontal, the vertical compared to the horizontal, but it will be in terms of theta, which is great because all of our independent inputs in polar coordinates are theta. So running through this, we're gonna do the exact same thing. We're just gonna go back and we're gonna say, all right, that dx over d theta, that was found to be cosine theta dr over d theta minus r sine theta. So we'll just take this guy right here. We'll copy him and bring him over. No need to do it again. And then going back over there, finding that dy over d theta, we'll take him and copy that and bring him back. And from here, we can now find the answer to our problem because cosine theta is a known thing. R is the given equation up here. And then dr over d theta can be computed from that. So let's just find those quantities. If this is r, then dr over d theta would equal 0 minus sine theta. Okay. So now, coming back over here, what we know is that dx over d theta, let me just give myself a little more space. Dx over d theta is going to equal the cosine of theta, now times dr over d theta, which we have found to be negative sine theta, minus our original r, which is 1 plus cosine theta, then times our sine theta. And that's going to be our dx over d theta. We can now go and find out what the dy over d theta will be. And using the formula we derived, it would be sine theta times dr over d theta. That's our same dr over d theta of negative sine theta, plus our r, which is 1 plus cosine theta, and then times our cosine theta. And that will be our dy over d theta. In order to find our dy over dx, we will take these two results and put them into a quotient with dy over d theta first on top. So that's going to be negative sine squared theta plus cosine theta plus cosine squared theta. And that's just simplifying this expression as I go. And then on the bottom, it will be the dx over d theta. So that's going to be negative cosine theta sine theta minus, and that's going to be sine theta minus sine theta cosine theta. At this point in time, we were asked to find the slope when theta was equal to pi over 3. So all of this should be evaluated at theta equals pi over 3. And then that would lead us to the final answer. But the one thing that I just really, really want to stress is that going back to the original examples we talked about, if you're familiar, if your students are familiar with these expressions, they have a very good foundation to work with when they're talking about polar coordinates, going back and forth, rectangular, polar. The questions that the exam likes to ask is rare you're going to see a graphing problem. If at all, you won't see a graphing polar problem, but you will see problems where they ask you to find the area in polar coordinates. That's a very common question, to find the area between polar functions, and then finding out the derivative and interpreting what that derivative means. Sometimes they ask for the slope of a tangent line, and that's a dy over dx. Other times they ask for a dr over d theta, and just remember, if it's dr over d theta, what they're asking is your radius increasing or decreasing? Are you moving closer to the origin or further away from the origin as the theta moves? So it's been just about an hour now. I'm very sorry for all the technical difficulties we've had this evening, but I appreciate you sticking with me if you've made it this far. If you guys have any questions at all, feel free to pop them up right now. I'm going to stick around for a few more minutes to answer any questions that come up. But other than that, I hope that tonight's provided you a good idea of how to use polar coordinates with finding slopes and areas and graphing. So thanks for joining me tonight. And like I said, I'll stay around for just a minute if you have any questions, but have a great evening if you don't.